Welcome back. This is the continuation of the Nature of Light Worksheet 4B, Special Relativity 2, focusing on length, contraction, and relativistic momentum. Previously, we have gone from this worksheet up to question 12. We are now going to focus on the last questions, 13 and 14. Right, so let's have a look at question 13. Question 13 says, a proton is travelling in a circular hadron collider with a radius of 500 meters, and it is travelling at that velocity of the speed of light. I think there are 6 nines in that. What is the strength of the magnetic field acting perpendicular to the motion needed to constrain the protons in this path? Okay, right. So to do this, we need to revise the Lorentz formulas for magnetic field strength. So the force on a particle, a charged particle in the presence of a magnetic field, is given by QVB sine theta. Now it says perpendicular, so it's going to be sine of 90, and that will equal 1. So we're going to look at this as just being QVB. Okay. Now, that force is the force that will make it go in a circular path. Okay? And this force will be the centripetal force. So we know that the centripetal force is mv squared on r. So the force needed, which is this one, must be supplied by the centripetal force there. So combining those, you get mv squared on r equaling qvb. We can cancel a velocity here, and we get mv equals qbr. Okay. So we've got to calculate the magnetic field strength. So we want to find B. Okay. So this here is mv, and that would simply be the mass of the particle traveling at this velocity. But we know that this is relativistic. This is not just mv. This is not Newtonian momentum. So this one here would be momentum at velocity, which is given by gamma mv. So I'm just going to put a gamma in that front of that one there. So we've got now gamma mv equals qbr. Another way of looking at this, which some people think is slightly erroneous, is that this is also, if I take the V there, gamma times m is the relativistic mass. It's the mass which has increased because of the velocity. Relativistic mass is a concept that is often discarded in relativity. We don't really like using it. We prefer to talk about relativistic momentum instead. But sometimes it is helpful in problems like this to look at these things here in this way. But since I've got the formula, I've got mv over here, which is momentum. I know that this stuff here, that is the momentum of a particle, and a relativistic momentum is given by that. Okay, so now I've got that. I can work out that B would equal to gamma mv on QR. So I need a few things here. I need to find, this would be m naught v, by the way, because that's the rest mass. This is the velocity of the particle, this is the charge of the particle, and this is the radius that we're traveling through. So I've got all this, I just need a gamma. The gamma would be 1 minus, this is a lot of numbers. There were 6. 0.1, 2, 3, 4, 5, 6 squared. Okay, what gamma will this be? This is going to be huge. Okay, 1 over the square root of 1 minus 0.12345 squared. 707.1069. I might just keep those numbers as a dot, dot, dot. Okay. So putting these values in, 707.1069 times m naught. Now that's the rest mass of this proton, which we now know in the worksheet, the rest mass. It's either found on your data sheet for the HSC, but we're also given it just here. So it's 1.673 by 10 to the minus 27 times the velocity. Now the velocity is 0.123456 times 3 by 10 to the 8th. Okay, all over the charge on the proton, 1.602 by 10 to the minus 19 times the radius, and the radius of this is 500 meters. Okay, let's have a look at what this gives us. Okay, so let's put all these values in. Let's see if I can move this up, so working space. Okay, so it's the top line. So it's 7, oh no, I don't need that. I've got that answer already there. Times 1.673 exponent at negative 27 times 0.123456 times 3 exponent 8 on the top. On the bottom is 1.602 exponent negative 19 times 500. Let's see if I've got that correct. Just check it before I press the equal sign. Looks good. Okay, so the answer is 4.43 Tesla. Okay, and is that the correct answer? I can't find question 13. It says it's supposed to be 44.4 Tesla. I've probably made a mistake somewhere here. So, yeah, that's what answer I get. Whether or not, I think it looks like I might have done the answer slightly incorrect. If you repeat my working and get this answer, great. Please let me know. If you get 44.4, I'll leave that on the answer sheet. I'm off here by a factor of 10, so I don't know where I have done that before, so I must have copied it down wrong. Okay, so that's question 13. And finally, question 14. This picture over here is got two graphs on it. Firstly, we've got a graph of velocity on the horizontal axis and momentum on the vertical. And Newtonian physics tells us that because momentum is equal to mass times velocity, it's simply going to be a straight line graph going up here. However, if we plot the formula for relativistic momentum, which says relativistic momentum is given by this, now that simply is PV equals gamma rho naught. It's not actually a P, it's a rho. That one there. When you put that into the formula, that's just going to be mv on the top times the gamma factor, which is what you've got here. Okay. So this is the graph here, and you'll notice that as v approaches c, the denominator becomes infinite, and as a result, we asymptote at the vertical asymptote of c here. Okay. So the first question is, what is the significance of the gradient of this here? Okay, so let's do that one first. Now, a graph has a vertical and a horizontal axis, and it's a straight line graph there. Okay, this is the momentum, and this is the velocity. Okay. So what is the gradient? The gradient is the vertical rise over the horizontal run. So the vertical rise over horizontal run is equal to momentum divided by, that will be measuring momentum. So this is the measurement of momentum. And the horizontal run measures velocity. Okay. So the gradient is equal to momentum divided by velocity. Now we know in Newtonian physics, momentum is mv, over v. So the gradient would equal m. And in this case, this m is not the m of the gradient, that is m meaning mass. So the gradient, which I'll give a letter k, is equal to mass. Okay, that's the first thing. The significance of the gradient here is that in Newtonian physics, that would be mass. Now, the difference in shape between the second question there is account for the difference in shape. The difference in shape here is that as we approach the speed of light, let's put another graph down here, move it up. As we approach the speed of light, our momentum becomes infinite. Okay? And if we were to take a tangent at any point, that tangent would be a measure of the mass. Okay? Because the momentum is always going to be gamma m mv. Okay? This is a velocity axis. So this is the momentum. So what is this tangent here? That tangent would be a measure of this section here, which is gamma m. And gamma m is a measurement of the relativistic mass. Now, once again, we don't really like the concept of thinking that mass actually does get larger. Remember, mass is simply the total mass that an object has is equal to the mass of its components, we'll call it the rest mass, plus the energy of the components divided by c squared. So this is the kinetic energy, how fast it's moving, and it's the kinetic energy divided by c squared. And this adds to that to give you the total. So as we get faster and faster, we have more momentum, we get more of this value here. And this is measuring that. Okay, so as we get to this point up here, our tangent is measuring gamma m. Okay, as gamma gets near infinite, because as we get closer to the speed of light, this factor becomes massive, then this tangent becomes near vertical. And as a result, we can't, as we approach the speed of light, we can't actually get there. Okay? And that there explains C. As we approach the speed of light, this denominator here would be 1 minus c squared over c squared. Now, c squared over c squared is 1. You get 1 minus 1. So the momentum would be infinite. Okay? As a result, the gamma times m would also approach infinity. Some people call this concept here relativistic mass. It really doesn't have an actual name or concept. It is just gamma times the rest mass. And sometimes we do call it relativistic mass. But it's a measure of the total mass the object has. Okay. Right, yeah, we'll leave that there. Thank you.